All right, welcome everyone to the first video this semester. This is going to be the practice exam solutions for the Unit 1 test of Physics 1402 E&M. Okay, so let's get started. One thing you'll notice about this test is this is a little more conceptual than a lot of the other, than the other tests that you may have had with me last semester. That's just because this material is a little bit more conceptual and less problem solving. If it were, I could have, a test that's full of problem solving stuff, but it's all going to be stuff from last semester, breaking down vectors and all this stuff that I hope you already know at this point. So now I'd like to kind of, test your understanding of the concepts and electricity and magnetism. All right, let it focus. There it goes. Okay, so the first question is an example of what I'm talking about. This is a really quick question. You'll see a lot more really quick questions rather than big time-involved problems. So anyways, for this example, we're looking at the ratio of the electric field at point B to the electric field at point A, EB over EA. So that's the electric field here and the electric field here. Well, if you remember the electric field from a point charge, that's just K, Q over, where Q is the point charge, over R squared, over K, Q, and I guess I would say that RB, over KQ over RA squared. Well, in this particular case, with this particular point charge, I guess I can go and insert the capital Q in there to show that now I'm putting a value in there, where RB is going to be 3L plus L, 4L. So instead of R, I'll put in 4L squared there. And EA is K, capital Q, and now it's just 1L squared. Well, we cancel a lot of stuff out. The K's cancel out. That's left with 1 over 4L squared over 1 over L squared. Well, you probably recognize that that is the same as saying L squared over 4L squared, which is L squared over 4 squared is 16 L squared. L squareds cancel out, so the ratio is 1 over 16. So when you quadruple the distance, you cut the electric field by a factor of 16. Hope that was a really easy one for you to show. In this case, this is just a quick problem. An electron traveling horizontally enters a region where the uniform electric field is directed upward. What is the direction of the force exerted on the electron once it has entered the field? Well, if you remember the equation for the vector equation for the electric field, oops, over Q, where Q is whatever force, that actually be a test charge. The thing is here, the electric field is going to be positive. Just write it like this, Q, E. The electric field is going to be positive, but the charge is going to be negative. So, and the charge Q equals negative E, so that's going to be negative E times the electric field, which means the force is downward. Now you can always remember that a positive charge moves in the direction of the electric field, and a negative charge just does everything opposite a positive charge does. I would like to, on questions like this, try to show something to show you understand what's happening there and you're not just guessing. I would appreciate it if you even write a sentence that says positive charge moves in direction of E, negative charge moves opposite. Something like that, just to tell me you know what's going on. Okay, so here's a little tougher one. Three charges are located along the x-axis as shown in the drawing. The mass of this charge is, I'm going to call this charge Q1, Q2, Q3. So that means Q2 equals 1.2 microcoulombs, negative microcoulombs, and M2 is equal to 4.0 times 10 to the negative 9th kilograms. Just write that down so I've got it. Determine the magnitude and direction of the acceleration of the charge when it's allowed to move if the other two charges remain fixed. Okay, so in this case we need to find what the net force is. I'll go ahead and draw the free body diagram. The force from this charge is going to be attractive, right, because it's a negative and a positive charge. So that is going to be in that direction. We'll call that F3 because it corresponds to Q3. And the force in this direction also attractive because it's positive. So we'll call that F1. Okay? So the sum of the forces on F2 is going to be F3 minus F1. And this is just Coulomb's law. So the F3 is K Q1 Q2 over R squared. And these are absolute values. Minus, and these are absolute values because I artificially insert the minus there, knowing that the two forces are in opposite directions. K Q3 Q2, let's say this is R21 and this is R23 squared, where R21 equals, so that's, well, these are a little out of sync. It looks like, okay, yeah, each hash mark is, gosh, is that? Yeah, each hash mark is 1 unit. So -5, -3, -1, 0. Oh gosh, I'm going to have to fix this. Yeah, all of these just got slid over. Okay, something to fix. All right, so R21 then is equal to, so that's 1, 2, 3, 4, 5, 6 meters, because X is in meters, and R23 is equal to 1, 2, 3, 4, 5, 6 meters as well. So R21 equals R23. And I'm just going to set that equal to R because they're the same thing. So with this, I can simplify this sum. I can pull out the sum of the forces is equal to K Q2. I'm dropping the absolute value signs because, you know, we know they're absolute values now. Over R squared because it's going to be the same in each one. So that leaves Q1 minus Q3. Now, what is the net force equal to? Well, that is equal to mass times acceleration. So then, the acceleration, I'm not going to calculate all this out, but Q1, Q2 over mr squared times Q1 minus Q3. And these are all absolute values. Now then the question says, what is the direction? Well, this charge is the same in each, but this is going to be the bigger charge, so it's got to go to the right. I made a mistake. I'm going to have to record this video over, I guess, because I wrote F3, but this should be Q3 minus Q1. Sorry, I may not have time to redo this video, but Just go with me here. So what you note here is this is F3 to the right direction minus F1. We assume the positive direction is to the right, which we know it's going to move to the right. It's going to move in the positive direction. So that means Q3, Q2, Q1, Q2, because Q1 is going to be smaller, and it's going to be to the left. And that means these errors propagate throughout, so it's going to be 3.1 minus 3.2. And when I throw this in the calculator, I know that's going to be greater than 0. So A is to the right or positive x direction. Okay, the next one. A point charge of this, of Q, negative 6 microcoulombs, is moved 1/4 of a meter horizontally to point P in a region where the electric field is 250 volts per meter directed vertically as shown. That's one thing to pay attention to. The electric field can be in newtons per coulomb, or the electric field can be in volts per meter. Okay, so that's something very, very important to note. What is the change in the electric potential energy of the charge? Well, you do know that EPE is equal to Q times the change in voltage. So we need to find the change in voltage here. Well, the problem is that equipotential lines, you may remember, are always perpendicular to field lines. So the equipotential is going to go like that. So we're not changing the potential. It's moving horizontally at a right angle to the field. So there can be no change in potential. So therefore, this is the symbol for therefore, change in EPE equals 0. So look at the units here of electric field. Well, this is a little bit different, but electric field says volts per meter. So if there's no change in the voltage, so there's no electric field in this direction. If there's no electric field in that direction, there can't be a change in voltage in that direction, and there can't be a change in potential energy. This is very much like on Earth, we have the gravitational field is uniform and downward, right? If we let a ball fall downward, the gravitational force does positive work on that ball. If we take a ball and we move it upward, positive work, the gravitational force, the work done by gravity is going to be negative because something's working against gravity. If we just move the ball from here to here, we've changed no potential energy at all because we have not moved, the field has not changed, the potential has not changed. So the potential energy has not changed. So this was a quick one. You will have a problem like this. So pay attention to this. Be sure you know how to work these. Okay, so the sketch below shows the cross-section of equipotential surfaces between two charged conductors that are shown in solid gray. This is the conductor, that's the conductor. And these are the equipotential surfaces. So this question says, how much work is done to move a negative 1 coulomb charge from A to E? So moving from A all the way to E. Well, if you remember, work is always equal to the negative change in potential energy. Or in this case, we're not worried about gravity or anything. We're just worried about the negative change in electric potential energy. And you know that the electric potential, the change in electric potential energy is just equal to Q times delta V. Because voltage or potential is the electric potential energy per unit charge. So multiply charge times change in potential, you get the change in electric potential energy. So I'm going to take this, I'm going to insert it there. Work equals negative Q delta V. Okay? So we have charge, Q equals negative 1.0 microcoulombs. That goes in there. We need to find delta V. So this is, let's see, 20, 30, 40. So this is plus 30. This is minus 40 volts. So work equals negative Q delta V, or V final minus V initial. So it equals negative Q times V final. Well, I'll just insert some numbers here. 1.0 times 10 to the negative 6th coulombs times V final, which is negative 40 volts, minus V initial, which is plus 30 volts. So let's see, this is 40, negative 40 minus 30, so that's minus 70. So the minus times minus is going to be plus. So work is going to be 70 times 10 to the negative 6th, and coulombs times volts is joules. So that's a positive number. Let's make sure it makes sense. That's a positive number because you're going from, you have a, oh gosh, I'm sorry, I keep making mistakes. This Q is negative. See, what I did there is I started looking at, does this make sense? And I started explaining why it makes sense, and it doesn't make sense. It's because I made a mistake. So this is negative, because the work is always negative change in potential energy, but the Q here is negative. So negative times negative is positive, times negative again is going to be a negative work. What that means is that the negative charge is moving from an area of higher potential in general to an area of lower potential. Well, a positive charge moves from higher potential to lower charge. A negative charge tends to go in the opposite direction. So if this is moving in this direction, then that means some force is having to push it out there. So the electric force does negative work because you're moving against the electric force. You're moving against where the electric force would try to push the particle. So that means the work is negative. So here we have a point charge gains 50 joules of electric potential energy when it's moved from point D to G. Determine the magnitude of the charge, D to G. Okay, well now we're just working backwards, right? So work equals negative change in potential energy, or negative change in EPE, or work equals negative Q delta V. All right, we don't know what the charge is, but we can solve for that. Point charge gains, well, we're gaining electric potential energy. So we would say that equals negative delta EP. I'm just copying that down, the negatives cancel. So the change in EPE is equal to Q delta V. I didn't have to deal with the work here. I'm kind of working in circles here. You could have just started with this equation. Anyways, Q is equal to delta V over the change in electric potential energy. The change in electric potential energy is given as 50 microjoules, not coulombs. And the change in voltage is equal to, well, let's see, we're going from D to G, so that is negative 10 volts to negative 50 volts. Actually, I'll just go ahead and write it out as V final minus V initial over delta EPE, just to make sure I don't miss any signs here. So the final is negative 50 volts, and the initial is negative 10 volts, so it's minus negative 10 volts. Okay, and the change in potential energy is 50 microjoules. So this is going to be, let's see, negative 50 plus 10 is negative 40 volts over 50 microjoules. So I'll let you do the math there. I don't have the calculator with me, but the charge is negative, which, let's see, does that make sense? We're going from Yeah. Let's see. Oh, yes, yes, yes. It's, so as the negative particle moves in this direction, it's gaining electric potential energy. That's because negative work, again, is being done on it. It's moving in the direction against the electric force, so it is gaining potential energy. It's very much like if you have a ball and you know, and we're talking about gravity. Gravity is working downward. If you move the ball up, you are going to gain gravitational potential energy, but the gravity is going to do negative work. Okay. All right. Determine the magnitude and the direction of the field at point A. Well, the way we're going to do that is we look at the change in voltage over the change in distance. Okay, so this is, well, let's see, it's uniform all the way across, and we have this measurement here. So let's do that. We know the electric field is change in B over change in S, where S is just displacement. So the change in voltage goes from 0, I'll write it out again, V final minus V initial over, change in S, where V final here is, say 40 volts minus V initial minus 0 volts, okay, and the change in distance here is 0.4 meters. Okay, so let's see, that goes in what, 100 times? Volts per meter is the unit of electric field. So it's 100 volts per meter, and it's pointing from and in this case we just know the magnitude from this equation. This doesn't give us the direction, but it's going to point in the direction of higher potential to lower potential. So it's actually going to point this way. All right, so this is the new stuff you haven't quite gotten a chance to work on. So let's determine the equivalent resistance for the circuit. All right, well, the first thing we've got to do is, well, I can't add this to anything else because all this is in parallel, so that's going to be tricky. I can't do this, but what I can do is I can work on this stuff. First, I'm going to label this R1, R2, and this will just make my subscripts easier, R3, R4. So if I want to find R3, 4, that's why I labeled all these. First I have to, because these are in parallel. These are parallel to each other, so the current's going to split there. So that's going to equal 1 over R3 plus 1 over R4. I'm going to write it a different way because when I put it in my calculator, this is easiest way to do it. So that's going to be R3 inverse plus R4 inverse, and the inverse of all of that. Or if you want to see the numbers, that's equal to 1 over, let's see, R 30 ohms plus 1 over 60 ohms. Okay, but I'm going to put it in my calculator like this. R34 equals 30 ohms negative 1 plus 60 ohms negative 1, and inverse of all that. record. So it's going to be parentheses 30, -1 plus 60, -1. I'm going to close parentheses and take the inverse of all of that. So that's 20. Probably could have figured that out without having to do that. So now I'm going to redraw the circuit here so I don't get mixed up. And I'm going to draw it over here, save some space. I probably should save more space. All right, so this is I combined these two into one, so that's R1, R2, R3, 4. Now, next thing I'm going to do is I'm going to say R2, 3, 4 is equal to R2 plus R3, 4, because these are in series, so I can just add them really simply. So R2, 3, 4 is equal to R2, which is 10 ohms, plus R3, 4, which is 20 ohms, which equals 30 ohms. I guess I didn't make this very systematic, but say I'm going to say 1, 2. Now I'm going to come down to 3. And this, now we're getting very much simpler. So I've got R1 and I've got R2, 3, 4. These are in parallel. So 1 over R1 is going to be equal to, R over 1, 2, 3, 4. So that's all of the resistors is equal to 1 over R1 plus 1 over R2, 3, 4, which equals 1 over 20 ohms plus 1 over 30 ohms, or if I write it in the way that my calculator does it so easily, 20 ohms -1 plus 30 ohms -1, and the inverse of all of that. So R1, 2, 3, 4 is equal to 20 -1 plus 30 -1. I'm going to take the inverse of all of that. 12 ohms. And what that circuit looks like is that. Okay, that wasn't too bad. What is the largest potential difference is across which resistor? Well, okay, so this is where I'm going to tear off the sheet. I'm going to go back and look at the stuff we did. Well, I have to work backwards and see what the potential difference across, well, first I need to find the current. So I'm going to start with this circuit here. This is circuit, call that 4. So if I start with circuit 4, where this is R1, 2, 3, 4, and this is the voltage V, which is 6 volts, then I can say the current through that and through the loop, I, V equals IR. So the current then is equal to V, I don't know, we'll call that V, we'll just call it V because that's the original voltage, voltage across the whole system. Well, let's do the same, let's keep order. Let's say V1, 2, 3, 4, that's the voltage across all of these resistors, the equivalent, represented by that one resistance there, over R1, 2, 3, 4, and that voltage is 6 volts over 12 ohms, so that's 1/2 an amp. All right, so 1/2 an amp is traveling right there, 2, 3, 4. I'll keep that 1, 2, 3, 4 to show it's going through the whole thing, and that's going to split up into 2 different voltages. So that's going to be I1 and I2, 3, 4. But then it's going to come back together and leave as I1, 2, 3, 4 again. Okay, you'll see why I'm doing this in a second. So now that I have the current through the whole thing, and I know that this voltage drop is going to be 6 volts because this adds 6 volts. This takes 6 volts away. Now I'm going to go back to circuit 3. I have R1, R2, 3, 4. Okay, so now I need to find the voltage drop across each one of these. And I know this is the current I1, 2, 3, 4 coming in, and this is going to be the same current coming out. I just need to see what this I1 and I2, 3, 4 is. Okay, well, the voltage drop across 1, we'll call that V1, is equal to I1, R1. Now here's a bit of information we got to know. We talked about this change in voltage over R123 being 6 volts because the power source adds 6 volts, the resistor takes it away. Well, we have to know that the voltage here and the voltage here are exactly the same. This is, 6 volts here. Or you could say this is 6 volts and this is, 0 volts, whatever. The potential difference is 6 volts. So this side has to be plus 6 volts and this side has to be 0 volts. So, and that's going to be same on each leg here. So then we could say the voltage drop V1 is, we didn't have to do anything there. We just say it's 6 volts. Now the question is, what is VR234? Because that's going to be I234 times R234. Well, we know that's going to be 6 volts too, because they both have to be 6 volts. So then it's easy to tell, well, we don't even have to go any farther because we know this voltage drop is going to be 6 volts, and all of these little voltage drops that form part of the circuit, they're all going to have to add up to 6 volts. So altogether, they add up to 6 volts in voltage drops. Well, this one alone is 6 volts. So that way, so in that case, the question asks, was the largest potential difference is across which resistor? Well, it's got to be that 20 ohm resistor. That one right there, the 20 ohm resistor. R1, it has largest delta V. Okay, so now the smallest current passes through which resistor? Well, we know I1 is equal to V1 over R1, and we remember, if we go back, we remember the voltage drop here is 6, delta V equals 6 volts. Because we know the battery is 6 volts, this side has to be 6 volts higher than that side. So this side is 6 volts higher than this side, and this side is 6 volts higher than that side. So we know the voltage drop across that is 6 volts, and we know the resistor is 20 ohms. So that's 6 volts over 20 ohms, which equals 6 divided by 20, 0.30 amps. Okay, so we got R1. We also can go back to, let's see, which one am I going to call it? R234. Let's go back to number 2. This is R1, this is R234. Okay, so the I234 is going to equal the voltage drop across R234 over the resistance of R234. So that then is equal to the 6-volt drop over the 234 resistor, which is 12 ohms, which equals 0.50 amps. Okay, so we see now that this is going to be a little bit higher current into this side, which makes sense because we said that the highest voltage drop is across this resistor. That's because this is larger than all of these resistors combined. So that means the current has to be greater through here. Okay, so now we've got our work cut out for us because we've got to figure out which one of these three resistors has the lowest current. Okay, so then we need to just go back to, oh, I'm sorry, this was 3 here. We need to go back to 2. Where this is R2, this is R34. We're not really going to care about R1 because we're just worried about this current in here. Okay, well, we know this I234 is going to equal I234 out, so the current through I2 then, well, it's going to be the same. Okay, so I2 is going to equal I34 equals 0.50 amps. But now we need to see what the voltage drop across R34 is, so we can then go back and look and find the current through each one of those. So the voltage drop in 34 is equal to I34 times R34, so that's 0.50 amps times R34, which we found to be 20 ohms. Okay, so let's see, that's 1 times 10, so that's, what, 10 amps? Yeah, 10 amps, that makes sense. 34 equals 10 amps. 10 volts, excuse me, 10 amps, I thought that was way too large. So we're talking about a voltage. All right, so going then back to 1, the very first circuit drawing, and I'm just going to draw this side. Okay, I'm going to extend that a little bit. So that's R2, R3, R4. Oops, I'm off the page. We know that this is I2 equals I234, which equals half an amp. We know that the voltage here, the potential difference here, is equal to 10 volts. All right. So then we can find the current through each one. So I3 is equal to V3 over R3. V3 is just equal to the 10 volts still. So that's 10 volts over R3, which is 30 ohms. So that's 1/3 amp. I4 is equal to V4 over R4, where V4 again is 10 volts, and R4 is now 60 ohms, so that's 1/6 amp. Okay, so putting it all together, I1 equals 0.30 amps, I2 is equal to 0.5 amps, I3 is equal to 0.33 amps, that's 1/3, just rounding, and I4 is equal to 1/6, which is half of that was, what is 1/2 of 1 divided by 6, 0.167 amps. So the smallest current passes through I4. Smallest. Okay, I want to go back, and I did make a mistake somewhere here. I've kind of corrected. Unfortunately, don't have a lot of time to, I wish I could correct my mistake, so so you don't even see it, but don't have a lot of time. Where is it? Oh, it's right here. Yeah, I wasn't looking at my equation sheet. There's a negative here. So that's why this wasn't making sense to me, because I knew the electric field had to point to the left, but this is positive, 40 minus 0, and this would be positive too. It's a positive change in distance, so it would be a positive thing, but the field is negative because I forgot that the equation is negative, and this is right because it points in the negative direction. And we know that, of course, because we define the x direction as, positive this way, so this would be plus 0.4 meters. The final position minus 0, the initial position. So it's a positive displacement. All right. I hope that helps.